Hello there, everybody. It's Andy Fowler here from Sigma-HSE. Hope you can hear me fine and can see the screen. And thank you for attending this webinar this afternoon, where I'll like to take you through issues around the basis of safety, which is a term that you'll undoubtedly hear a lot about, especially in the UK. But I just wanted to put a bit more meat on the bones as to what's meant by basis of safety. So just to introduce myself, I'm currently the Technical and Operations Director at Sigma-HSE, and you can see my background there. So I am a chemist by training, decade in the chemical manufacturing industry, handling lots of different dangerous chemicals and processes. I've also been 17 years in the UK Health and Safety Executive as a process safety specialist, inspector and risk assessor. So in my time, I've seen an awful lot of different types of processing operation within the UK and further afield. And you can see I was also the author of some HSE guidance documents that are still available even now, although there'll be slightly different editions because, of course, the legislation changes. But the one that's really pertinent for today, I guess, is the safe design and operation of chemical reaction processes. Still available, still freely available for download from the HSE website. Particularly proud of that one. It's one of my favourite pieces of guidance there. And I'm sure you're all aware of the Sigma-HSE Group, a global company with offices in the UK and India, offering not only consultancy on process safety, but we've also got extensive accredited testing facilities for determining flammability and electrostatic data and so on, and also use our knowledge and experience to offer training courses, whether they're bespoke or in-house or standalone training courses, open training courses for anybody who attend, which is what basically this webinar is about today. So, you know, we've got a team of highly qualified engineers, scientists. Some people sit on standards committees, and we've all tended to work within the process industries in one shape, form or another. And of course, we've got the resources of the laboratory for our fire explosion testing and so on. So we can offer quite a large scope in terms of the things that we're interested in doing, and things that these days perhaps many industries, many companies on their own have limited experience in some of the tools and techniques that we use to get a grip on many of these assessments and understanding of hazards and things like that. So what I'd like to do today in terms of, you know, the next hour is talk about basis of safety, and I'll start off just by trying to be as very simple and as holistic as I can be on what is the basis of safety, to make it clear in everybody's mind and what we need to understand and what knowledge we have before we can develop that basis of safety. And we'll then have a look at standard, if I can call it that, basis of safety, because like with everything, there's many ways of doing things. It's the same with basis of safety. There's many options you can take within our processing operations, and I'd just like to take you through some of the accepted best practice really where basis of safety is concerned. So really the definition of basis of safety is a combination of measures, safeguards, barriers, call them what you like, that we rely upon to ensure our safety, to give us some protection. Because, you know, on the whole, in the processing industries, we do handle a lot of hazardous materials by definition, and sometimes at quite severe operating pressures and temperatures and things like that. So there is the scope in many of the processing industries to do a lot of harm, either to ourselves as humans or to the environment or indeed to the business. Okay, so the basis of safety is all around putting in place measures, barriers to prevent, control or mitigate bad things that could happen. So clearly, to be able to have a sound basis of safety, we need to understand what can go wrong, because it's only with that knowledge of what can go wrong, our hazard identification and our knowledge about the hazards and when those hazards may become realised, can we then consider putting in place measures and what types of measure to deal with these things, either to prevent the hazards in the first place or to control and mitigate them if those hazards become a reality. So really, it's all about getting to grips with what I'm going to call the safe operating envelope. And the processing industries are pretty darn good at understanding what the safe operating envelope is. Many of you in your companies will manufacture substances, products, or whatever. And you need some control to be able in your manufacturing processes to end up with the product that you require, that you can sell, that fully meets your specification, that is of the correct quality, is of the correct yield, and so on and so forth. Yeah, and we tend to design our systems with some element of that safe operating envelope, because we know if we need to make chemical X, we need to keep the temperature under control and the concentrations under control and so on and so forth. And that's our safe operating envelope. And generally speaking, for the vast majority of time, we as humans, either through manual intervention on our processes, or generally these days our SCADA and our DCS instrumentation systems, keep us within our safe operating envelope. We monitor temperatures and the system opens and shuts valves accordingly to keep us within the safe operating envelope, and then we end up with the product that we require in the yield that we want at the quality that we want and everything else. But of course, if we go outside of that safe operating envelope, we need to understand what I call the potential excursions. If we go beyond the safe operating envelope, if the reaction starts to get too hot, if we suddenly comes across a flammable vapor, suddenly comes across a source of ignition, you know, we've got to understand what that means, because it's on this basis, because this is what can go wrong. It's on the basis of our potential excursions that we need our basis of safety measures to either prevent, control or mitigate these potential excursions. So they're all relatively rare, because otherwise we'd be making bad product all the time and so on. But it's understanding these potential excursions. What can go wrong? Does the chemistry change? For instance, do we suddenly start operating within flammable limits? All of these things are potential excursions that can put us at risk of some serious hazards, of having fires, of having explosions, of having chemical exothermic runaways, or having decompositions, and all of these sorts of things, which really we don't want to happen because it stops our manufacturing processes, but of course it can do a lot of harm. So it's with this knowledge that we then put in place the measures to manage these potential excursions, to try and stop us from getting there or dealing with it if we do. And of course, just like everything else, it's not just a technical basis. There's a lot of management there. There's a lot of communication that people know what they need to do correctly. What happens if something goes array in the process control, how to handle it, how to deal with an emergency, how to operate some of the basis of safety pieces of equipment or whatever. So there's a good element, as with everything in health and safety land, of management practices. So the basis of safety is built up about this knowledge of the safe operating envelope, which, as I say, we're generally quite proud of and quite knowledgeable of. And of course, to keep us within that safe operating envelope, we'll have items of equipment that help us, that keep within that basis. We'll have procedures that we follow, whether we're doing maintenance or operations or whatever, to do things correctly. We need to understand how we're going to detect that we're starting to deviate from our normal operating conditions or processes. You know, this knowledge, these potential excursions I've been talking about. Of course, people are involved, so there's an element of human factors there. Do people know how to operate these barriers that we've installed as part of our basis of safety? Have the designers design them correctly? Do the maintainers maintain them correctly to make sure that they're effective? Because after all, you know, these barriers, these measures that we put in place, on the whole, should never operate. They're there to give us that protection if we go beyond our safe operating envelopes. And very often, you know, going beyond these safe operating envelopes are very infrequent. You know, these are often our last lines of defense before something goes really bad. And of course, we've got to understand that the properties of our materials that are used, because often many of them are classified as dangerous. So all of these things fit in, as well as an understanding of, well, yes, we can't really eliminate all hazards and all risks from hazards. There's a certain level of risk tolerance that your company wants to take, or the regulator wants us to take, because we don't want to be wasting money reducing risks that are already acceptably low. So there's an element of making sure that, yes, we can keep adding these barriers, but we need to satisfy ourselves when enough is enough. When we've satisfied ourselves that the barriers that we have got give us the level of protection that we require. And of course, there's many more aspects of it, especially if you're if you're a site that's got significant major accident hazards. The demonstration of this control, the demonstration that the design basis and the basis of safety, and that the equipment, that the barriers that you've installed will be effective when called upon, is, and you know, if you have to produce a safety report or whatever to put in front of the regulator, that demonstration is quite intensive these days. That demonstration, that justification that what you've done is sound and reduces the risks from those hazards down to an acceptable level. So basis of safety is very important, but we'll get a bit more specific now, because if you look at the ATEX legislation in Europe, or in the UK, the DSEA legislation, the Dangerous Substances Explosive Atmosphere regulations, those set of regulations specifically use the term basis of safety, and it's a basis of safety to prevent and manage fires and explosions. That's what those regulations are concerned with. And when you look at them, you know, if you just think about it logically, fires and explosions come about when we allow the fire triangle to be joined up. That simple little triangle that says, for something to be able to combust, we need to have a fuel, we need to have air or oxygen, and those two need to be within certain proportions. Otherwise, they'll be too lean to burn or too rich to burn. And then we need an ignition source. So of course, if we're within the flammable limits of a flammable liquid or the vapors from a flammable liquid, one obvious way of preventing an ignition is trying to avoid generating those flammable atmospheres, trying not to work within the flammable limits. Okay, that's one way we can prevent ignition, is to prevent having a flammable atmosphere. And generally, again, in many of our processes, we're pretty good at that. In our processes, many processes avoid mixing air with fuels. The fuels are generally, liquid fuels transported around the place in pipes and in reactors and what have you, don't come across an atmosphere. We don't deliberately mix them in air and things like this. But of course, if we have a loss of containment, where we let the fuel get out into the natural atmosphere, that's when it can mix with air, that's when we can generate flammable atmospheres, and then if we have an ignition source, we can end up with a fire or an explosion. Okay, but the third point of the fire triangle is having an ignition source. So of course, if we can avoid ignition sources, we break the triangle again. It's difficult though, when we're looking at processes, to eliminate all potential ignition sources all of the time. We do our best, but generally speaking, chemical engineers and so on are brought up to believe that avoidance of ignition sources is perhaps the lowest end of the safety triangle to try and prevent explosion. It's a lot better not to have flammable atmospheres generated in the first place if we can. And then of course, so we've got two ways there of trying to prevent a fire or explosion. Don't have a flammable atmosphere, don't have a fuel air mixture, and don't have an ignition source. That breaks the fire triangle. But of course, it might still happen because we exist in a life that's risk-based, so we can do our best to avoid creating a flammable atmosphere. We can do our best to avoid having an ignition source. But occasionally it will happen. And therefore, if there is an ignited event, we need to make sure that we can protect ourselves from those fires and explosions. So we're not sending missiles around the plant or off-site, which could harm people and damage assets and so on and so forth. So there's an element of explosion protection as well built into the basis of safety. So in terms of explosion prevention, we can limit the risk associated with handling fuels. Can we use a fuel that's less flammable or non-flammable if possible? Because clearly then we can't have a fire explosion. Can we mix a non-flammable material in with another liquid to increase its flash point? Just simply adding water to alcohol increases the flash point. If we're dealing with powders where dust explosions could be an issue, then can we work without having fine powders? And one of the best ways of doing that is to keep our powders in damp or paste form. They're not so easily raised into a cloud to form that flammable atmosphere. Or not having very dusty powders, deliberately using pellets or granules rather than powders. And of course, we can also, again related to the fire triangle, we can keep below the minimum explosible concentration for powders by making sure there's more air there, so there can't be an ignition because there's too much air, it's too lean to burn. We've reduced the fuel concentration when we make a dust cloud to the point where it's not ignitable. And we can do the same for gases and vapors. If we can work below the flash point, below the lower explosive limit, or even above the upper explosive limit where it'd be too rich to burn, we can protect ourselves. So even if we've got an ignition source, we still won't end up with an ignitable event. Or of course, we could inert the atmosphere. Again, take the air out of the system, operate under vacuum, operate under nitrogen or CO2, and so on and so forth. So there's many things we can do, but we need to focus our minds to it. It's very easy just to do what we've always done. You know, we've got toluene on site, so that's our solvent that we prefer to use because it's there and it's ready and we're used to handling it and so on and so forth. Really, we need to get out of that mindset and think more about, can we avoid having the fires and explosions? Do we really need a low flash point solvent like toluene? Can we get away with something that's higher flash point? And so on and so forth. So they're quite fundamental questions. We've got to remember that if we're working with combustible dust, really it's not possible to remove the fuel. It's going to be present. Even with most powders, you know, it's all a function of the particle size distribution. As I said on one of the earlier slides, the powders are okay if they're larger than about 500 microns. But of course, many powders, attrition can occur and breaks down over time, or if you're transporting them in screw conveyors or pneumatic transfer lines and things, you can end up, if the powders are very capable of attrition, of breaking down and creating more dust. So it's a bit difficult to move the fuel. For gases and vapors, we can do this by having sufficient air that we're below the flash point, below the lower explosive limit, and ensuring that our systems are working under that way so we can't have an ignition. And some processes do work above the upper explosive limit. Lots of printing processes are designed to operate above the upper explosive limit when they're handling solvent-based inks and so on. Although, as you can imagine, these days there's a lot less solvent-based inks and that in processes used than there used to be. There's many more water-based systems now and cleverer systems, which has inherently removed the possibility of a flammability issue. So, of course, you can tell that we need to understand whether the substances that we're using, we need to know what the LELs and flash points and so on are of our materials, because this is important. This tells us what we need to do to process them. This will decide what barriers we need as part of our basis of safety. And of course, as I said before, we can inert, but the inertion's got to be good enough. With how much oxygen is required for a given substance to burn or explode is dependent on the specific substance. It's called the limited oxygen concentration, or the maximum permissible oxygen concentration, which if you're using inertion, you need to be below these values and know that you're below these values to guarantee to yourself, to give yourself that justification that you have reduced the level of oxygen in your systems down to a level with a safety margin which won't ignite. And then you're protected against the fires and explosions that could occur. When we're looking at explosion protection, when we try and put things in place to deal with having the ignited event, these are generally done for fires and explosions in three ways. We can either contain the explosion, we can vent the explosion over pressure to a safe location, or we can suppress the explosion. We can inject extinguishant into the incipient explosion. Okay, but with all of these techniques, because we've got different bits of equipment generally in series or in parallel linked to each other, we've got to have means of isolation to stop the flame front or the explosion pressure trundling off into the next piece of equipment upstream or downstream, because we've got no isolation. And of course, there's different ways of doing this, and I'm not necessarily going to go into the detail of the different levels of containment. I think it's self-evident. Containment, we have a knowledge of what the maximum pressure and the rate of pressure rise is if we lose control and we have the ignited event, and we make sure that the containment system can withstand that maximum pressure and that rate of pressure rise. So nothing comes out of the containment vessel. The explosion's contained within it. But that, of course, requires big, beefy equipment, pressure systems, and that pretty heavy stuff that'd be very expensive to manufacture and to look after throughout time and so on. What is very common in process industries is having venting, relief panels, whether that's a bursting disc or a pressure relief valve on a reactor or a vent panel on a dust collection system. Okay, it's just an area that makes sure that that venting allows the pressure within the containment system to be a lot lower than it could be if it was just contained. And we vent that pressure as well as generally a dirty great big fireball out of a hole. So of course it needs to go to a safe place, preferably somewhere outside and so on. And explosion suppression is becoming more and more used in the industry, although it's still quite expensive and it requires specific knowledge on how to design these systems, because it all relies basically on a good detector system that picks up the incipient explosion or fire very quickly and then can act then to essentially fire off a fire extinguisher that puts it out. So, you know, you need a detector system that is very effective, and then a good form of injection into the piece of equipment to be able to do the job. But the systems are out there, they just need careful design. When we move over onto the explosion prevention via the avoidance of ignition sources, if you look in the DESIR ACOP and the standards that are out there, it mentions 13 potential ignition sources, because really any electromagnetic radiation could potentially be an ignition source. But these 5 here are the most common ones. You know, hot surfaces, pretty obvious. We all know that hot surfaces can form, or naked flames and things are a good source of ignition. We all know that sparking electrical equipment, poorly installed, poor wiring. We all know electrostatic discharges that give us a spark could cause an ignition, and of course mechanical sparking when we get friction between 2 surfaces and things. These are still basically the primary means of having potential ignition sources becoming live and then causing us a problem. But as I say, process safety specialists tend to work on the premise that just basing our basis of safety purely on elimination of ignition sources is something that we don't feel comfortable with, because it's very difficult to eliminate all potential sources of ignition all of the time. But it's important that if we do get that ignited event, things can get a lot worse if we don't have this isolation between items of equipment on our plants. You know, if that fireball and overpressure can go down ductwork into other pieces of equipment, the pressure by things called pressure piling and things can essentially be a lot higher than what it was in the first place. So you might have a P max, for example, maximum pressure developed in an explosion in one reactor that's, let's say, 8 bar. But if that was to go through to a similar reactor, because they're connected, because of this function of pressure piling, you might see 10 or 12 bar in the second reactor. So even if it's rated as 8 bar, it still won't do the job. So having this rapid isolation, and we can do that in a number of ways. Quick acting valves that will require some detector system again to shut. rotary valves on powder handling systems, chokes within our screw conveyors on powder handling systems will all give you that isolation, will prevent that explosion pressure or fire, flame progressing down from one part to another. But of course, we must have that knowledge of what do we need to do to be able to get ignition. So the sorts of data that's really important to us when we're dealing with gases and vapors and trying to avoid fires and explosions is to have the knowledge of the flash point. You know, that's the flash point being the lowest temperature at which a liquid will give off sufficient vapors, which if it comes across an ignition source, it will flash. And if your flash point is less than ambient temperatures in the UK, that means if you spill it, if you have a loss of containment, it will give off sufficient vapors to be above the lower explosive limit. So if there is an ignition source, it will become readily ignitable. Okay. Auto ignition temperature is another important parameter where we can use to make sure that equipment that runs hot, it's not hot enough to ignite material. Auto ignition temperature it's auto ignition. It's release of the substance at above that temperature will ignite. It doesn't need a separate source of ignition to ignite it. You've got to be careful with auto ignition temperature. You'll find them be easy to pick up auto ignition temperatures from the literature for all manner of solvents that we use in the process industries. And they're pretty high. They're generally around 400 degrees and this sort of thing. I mean, I think the auto ignition temperature for something like hydrogen is around 500 degrees C. But the problem with auto ignition temperature, the quoted values, is it's an auto ignition temperature under defined conditions in a specified test. And release of your material on a processing plant isn't under such defined conditions. And effective auto ignition temperature can differ very widely from what the literature tells you. So for instance, a release of hydrogen from pipe work with a decent bit of pressure behind it, it will auto ignite if it comes across a lot of impingement on pipe work and things at temperatures a lot less than 500 degrees C, and perhaps 100 or 200 degrees lower. Okay. The LEL and the UEL defines when we can become flammable, so we can protect ourselves by working above the UEL or below the LEL. If we know this, we need to understand the vapor density, because if the stuff gets out, you know, does it sink and just spread across the ground, or is it very buoyant and just disappear off into the air? Okay. So, and also, as I mentioned before, how much pressure is developed if we have an explosion. We need to know that if we're considering things like venting or containment or indeed suppression. We need to have some idea of the rate of pressure rise and the maximum pressures to be able to design our explosion protection systems correctly. When we look at powders and dust, it's a bit more involved, but again, it's just measurements, and there's an awful lot of physical data out there for flammable vapors and liquids and gases. Awful lot. You don't really need to do much testing. But where powders and dusts are concerned, there's less available in the literature, and what's quoted in the literature really gives you a false sense of security, because the problem with powders and dusts is it's the particle size distribution and the amount of dust that's present and how readily that dust form into a cloud. And if you find, when you look through the literature for things like minimum ignition energies, minimum ignition temperatures of standard materials, if you like, flour, wood dust or whatever, you'll find that they never quote what the particle size distribution is. So it's always best with powders and dusts, if you're using particular substances, is to get those specifically tested in laboratories to get at these figures. Because of course, you know, in many respects, the minimum ignition energy is what it says. How much energy do you need for this particular material? How much energy is necessary for it to ignite? And that can range from tens of joules down to literally 1 or 2 millijoules. There's a big difference. Some things are a lot more frisky than others. And it's the same with minimum ignition temperatures. Some things have got to be really hot before they'll ignite. Some things will go at relatively benign ambient temperatures. We can all get at this sort of information from the testing of the material properties. Now, just moving on, so I've looked at fire and explosion there, but basis of safety is also important when we look at our reactive chemistry. Because again, we need our basis of safety there. We need to have measures in place to be able to deal with our excursions from our normal reaction chemistry. Because if we can lose control of our reaction chemistry, all manner of things can change. Kinetics can change, thermodynamics can change. We can change the chemistry altogether and make totally different materials. I mean, for example, if you remember the Seveso incident in Italy a few years ago now, but what they were doing, the normal chemistry they were doing was quite benign chemistry, not really using any dangerous substances. But if it got too hot and it went into exothermic runaway, the chemistry then changed and they started producing dioxins, which are very toxic materials. And although they didn't blow the plant up because it was protected against pressure via a vent on the reactor, of course, because the chemistry had changed and made all these dioxins, it was those that were sprayed out of the vent all over the neighbouring countryside, which harmed people and harmed the environment. You know, so it's this understanding of what can go wrong. And so I just want to spend the last part of this session looking at the different ways of basis of safety within chemical reaction processes. And the first way is to think inherent safety, where if we lose control, would it cause a hazard? Now, it's often considered a theoretical concept, inherent safety, because that's really, you know, as humans, we don't like changing. If we've always made this stuff this way, then this is the way we'll always do it. But it's about questioning, can we do things that are inherently safer? Can we eliminate those hazards? We can only do it at the really early stages. It's a technique that chemists should be more and more involved in, looking at inherent safety. You know, do I need to use a high volatile solvent with a low flash point? Could I get away with one that's a higher flash point? Can I use a catalyst in the system rather than having to operate at high pressures and high temperatures? Yeah? And very often, if we can design out hazards, remove hazards, our plants are a lot cheaper to build, cheaper to operate throughout the lifetime, because we're not having to put all these measures in to deal with these hazards, which we generally build into our processes. So inherent safety is around specifically thinking about, can I substitute this material? Can I use a higher flash point solvent? Can I operate at, do I need to operate at pressure? Can I minimize the quantities? And this is where we have done a fair bit of work over the years. Now it's very rare now outside polymerizations really that we see batch reactors where we put all the ingredients in the reactor, shut the lid, warm it up and let it go on. We tend to use semi-batch and increasingly continuous processing for our chemical reactions. And these allow us to minimize quantities. So, you know, I can't have a release of 10 ton of a toxic material if basically I've only got 2 kilos of it floating around the reactor system at any one time. Can I moderate it? Can I use catalysis to help us operate at lower temperatures or lower pressures? And can we try and keep it simple? Yeah, it's something which just requires a different thought process in the early stages of process design. It's a nice to have. It's something as we go through life we need to focus on more, and we're being pushed to do this more in Europe, at least by the regulators. But it's fair to say, you know, it's not common to put new processes in anymore, so we have to live with our existing processes. So we need to understand the basis of safety that's there for our existing processes. And I've just given this simple little example here, and I've come across this numerous times. Reactors are heated by steam. Here's one. It's got 300 degrees C steam input to the jackets and that on the reactor. And they're doing chemistry where they want to do the reaction at 85 degrees C. One of the excursions you'd look at, and they knew about, was if the reaction mass got up to 160 degrees C, they had a thermal decomposition that resulted in a lot of gas generation and a runaway reaction. So something they tried to avoid. So they did lots of work and put in big relief vents on the reactor and everything else. If they'd have simply plumbed the reactor cooling heating system to use hot water rather as the heating medium rather than steam, hot water can't go above 100 degrees C. You've got a comfort margin of 160 degrees C, of 60 degrees C before your onset temperature for decomposition. You've effectively eliminated the possibility of that decomposition. It's inherent safety in practice. We need to get used to this. You know, the only reason why the steam on that reaction, on that actual reactor that was used for this product, was because that's what it was plumbed in as and had been for years. When we look at this, the same concept with our reaction chemistry. I mentioned before about safe operating envelopes. It's understanding that chemistry, the boundary that keeps the control reaction. Not only will it be safe within the safe operating envelope, it'll be productive as well. It will give us the material in the correct yield, the correct quality, and so on and so forth, if we keep tight control of the safe operating envelope. But it's this excursion beyond it. And when we're doing reactive chemistry, that those excursions are going to be related to things like the thermal instability of the reactants or the mixtures or the products or any of the intermediates or whatever. What happens if these products get too hot, essentially? Are they exothermic reactions? Many of our reactions that we do in the processing world are exothermic reactions, so they raise the temperature. If we get exothermic runaway, does it lead to a decomposition or simply violent boiling? Or do we start generating gas and so on and so forth that we've got to deal with? We've got to understand how far we are from our normal operating conditions against some of these things happening, against the materials falling apart, against getting violent boiling, against getting decompositions that generate gas. And then we can put in measures in place to make sure that we're operating below these so they don't happen. And you do this by what's called your chemical reaction hazard testing, where you test under adiabatic conditions. And what that means is you use calorimetry to try and reduce the losses of heat that you may have, keep the heat in the system, which gives you the worst case. In the laboratory, when we're using glassware and things, an awful lot of heat of reaction are simply lost through the walls of the test tubes and the flasks and what have you, that we end up having to heat the reaction. Once you start putting them in large volumes on plant scale operations, that heat that heat loss is minimized greatly, and a lot of that heat remains within the reaction mass, which you've got to somehow get rid of or control. Yeah. So doing our testing our reaction chemistry, where we can say, well, what happens if the reactor stopped during the reaction and then the operator turns it back on, or if there's insufficient cooling, or if we charge the reactants in the wrong order, or put too much in, or not enough in, or whatever, or at too high a temperature or too low a temperature. It's this sort of knowledge we need to know so we can find out what's going to happen in terms of the excursion, and then with that knowledge we can put in place our measures. And our measures would be, for example, using heating mediums where the maximum temperature doesn't cause any of those things to happen, or putting restricting orifices in our feed systems so we can't put too much material in, because in a semi-batch situation what you're trying to do is feed in one of the reactants at a rate where it's consumed almost instantaneously in the reaction mass. We're trying to avoid what's called accumulation. Okay, so if you start getting accumulation, and that's exothermic reaction, you start developing heat, all you need to do is shut off that feed and the reaction will automatically die and the temperature will come back down, you'll come back into control. You can't do that on a batch installation where you put all the ingredients in, shut the lid, and then put the heating on. If that thing decides to exothermically react and the cooling fails, for example, there's not a lot you can do. There is, and I'll discuss them in a minute. But generally, it would be better if you could feed in one of the materials at the same rate that it's consumed. Then if you do get temperature excursions or pressure excursions, you can simply shut that feed off and you kill the reactor. Yeah. So there's many ways you can do it, and we'll look at those now. Once you've got that knowledge, then when we look at our different basis of safety, that knowledge will, that data that we've got will allow us to choose an appropriate basis of safety, which might be relief, it might be installing very good process control systems, but there's many other ways that we can stop excursions from reactions occurring, crash cooling, quenching, and so on and so forth. And we'll just have a little look at these. Now, obviously, we'll have process control on all our chemical reaction processes, and whether that's operators just running around opening and shutting valves in sequence or whatever, or these days generally it's SCADA systems and DCS systems with alarms that tell us when it's getting too hot or the pressure's going up or so on and so forth. So it is possible for your basis of safety to be process control. It might have to be very high integrity process control if that's the route that you're going down, and you may end up having to put in safety instrumented systems and a functional safety management system and everything associated with safety integrity level equipment and all of that. But it can be done, because all you're really doing is putting in high integrity, or turn it around the other way, high reliability stuff that should stop these excursions from occurring by using process control. So the sort of information that you need to be able to do this properly is good understanding of what your optimum process conditions are, what your safe operating envelope is, and the impact of maloperations on that. Good understanding of onset temperatures of anything that's undesirable. What's the onset temperature of a decomposition, or onset temperature of an exothermic reaction, these sorts of things. Or temperatures below which you don't get that reaction. You may be feeding in a chemical at a certain rate that should be consumed at a certain temperature, but if it's not consumed because the temperature is too low, or it doesn't mix in the reactor as well because the agitator's off when it should be on, you can then result in accumulation. Then, of course, if the temperature goes up or the agitator switch back on, you get more rapid reaction, and that's when you can get runaways and things like this. So it's understanding, and you can do all this through the calorimetry and what have you, what happens when we have reactant accumulation. And then we'll feed that into our basis of safety with what type of reaction mode will we use? Batch, semi-batch or continuous? And it's safer the more you move from batch onto continuous on the whole. Putting simple things like orifice plates in addition lines or other flow control measures, having interlocks and cutouts, etc. Fail-safe coolant supplies. But of course, there's a lot of work here if you're relying purely on process control to prevent these things from happening, that whatever these measures are, these barriers that you put in as part of your basis of safety, you'll have to do a lot of justification to make sure that they're reliable enough and they're not, you know, that we can't have common mode failure and such things as this that reduces their reliability of working. But it can be done, process control. And invariably we'll have some level of process control on any reactive process. But we can also have process control plus containment. We talked about containment being one of the basis of safety. Basically, if we do have a runaway reaction or a decomposition or whatever, it doesn't matter because the reactor and everything that's hanging off the reactor is rated to a pressure higher than the pressures and temperatures that could occur under that runaway situation. It's as simple as that. But clearly you need to know what is the worst case scenario, what could develop the highest pressure. Yeah, and you need to get at that sort of data by doing reaction calorimetry, by doing it on the worst case conditions, which is adiabatic conditions. So essentially removal of heat to atmosphere through process plant is taken out of the equation. And then you can simply build your pressure vessel and everything, all the ancillary equipment to deal with it. So it's a recognized way of doing it, but it's not very common. We can also control systems by having process control and crash cooling. So if we start having a runaway reaction or a decomposition, we effectively have some emergency cooling facilities. And of course, you need to know how much heat you need to take out of the system to stop the reaction. So you need to base that on the worst case scenario. You need to have some understanding of how the power output profile between your heating and cooling curve occurs through on your plant. So it's calorimetry time again. Calorimetry time again. But you need that to make sure that whatever cooling, your emergency cooling, crash cooling does, it's got to be good enough. It's got to take out the heat that is necessary to take out the heat. So once armed with that information, we can then select how we're going to cool the system, select the cooling medium, which in our world is usually water, but doesn't have to be. And then, of course, don't forget, you've got to have a system that picks up and can activate that cooling system. That needs to be of sufficient reliability. You can't build this sort of system and rely on an operator to pick up that the temperature's gone too high and then open a valve. That's not what's required by a basis of safety, which is using process control and crash cooling. Another way of doing it is to simply get rid of the contents of the reactor. So if something array starts to happen, we start temperature and pressure start going up, we can either quench the reaction, we can add a cold diluent to the system that will take the heat out of the system. Of course, to do this, you need to have Your reactor needs to be big enough to take this quenching liquid. It needs to be put in rapidly and at the right point, or we can drown it out so we can dump the reaction contents into another vessel that already contains this cool diluent. Okay, or we can do what's called dumping. We can simply dump the reaction mass into a larger vessel, and just by virtue of doing that, we reduce the temperature, and if we have a large hullage space, we'll reduce the pressure. This is often used with relief as well. Often you'll see a dump tank on the output from a relief system. So the reactor is relieved into a dump vessel, and within the dump vessel, the reaction is effectively killed. So that's another way of doing the job. We could also use reaction inhibition. What this basically means is detecting something. So we need to stop the reactor. We've detected something's going wrong. Now we put something into the reaction mass that inhibits or kills the reaction. And this can be done. Again, we need to understand what the worst case scenario is and try out different types of inhibitor under worst case conditions. It's got to be we've got to make sure, because we're injecting it in, that we get good mixing and all the rest of it as well. So that determines how many injection points we need and where they need to be. But they are installed in systems out there. But again, they rely upon this high integrity detection system. So it's always process control plus reaction inhibition. And then the one that we normally see on our processing plant is a vent. So we simply vent the contents of the reaction to a safe location. And again, to do this properly, to be able to size the vent that's necessary, the area of vent necessary, needs to be based on knowledge of the worst case scenario, knowledge of the reaction kinetics, temperature pressure relationship. It's calorimetry again. Calorimetry under adiabatic conditions is the testing that we need to do. We can do some calculation on this, but we really do need experimental testing, really. Venting, there's different types of venting phase. We can have different means of different types of venting, whether it's just venting vapor or it's venting froth. If you think about boiling water and compare that with boiling milk, well, those two extremes can occur in your reactor masses. You might just get vigorous boiling like water and we just generate steam and off we go. You might get like boiling milk, where you get a many-fold increase in volume, you get swell, and you get a foam. And all these sorts of things impact how you size that vent. Because if the vent isn't adequately sized, it won't be effective. You'll still end up potentially blowing up the reactor system and sending missiles around. So just because you've got a vent, like with everything, these things have got to be effective. They've got to be properly designed to do the job, and to be able to do that properly, we need that data. There's a lot of data that we need. So just to finish off, in the last couple of minutes, I've just got a last few slides on all of this. Of course, your basis of safety needs to be worked out, justified, written down, used and kept within the business, and not forget. And so that allows you not to forget as to why that, what that vent was designed for, how it was designed, what data was used, what the calorimetry was, and all the rest. And my experience is an awful lot of industries, processing industries, they've got the basis of safety, but they've lost the knowledge. They've lost the calculations that were done. They've lost the calorimetry reports and things like this. Okay, so we're lacking there. A good system will have policies and procedures that push you to identify chemical reaction hazard testing, especially for reactive chemistry. It will push you for how you're going to identify flammability testing, and so on and so forth. And of course, your management system needs to be good enough to act as a good knowledge management system. All of this comes back, if you think about it, back to understanding what can go wrong, and that comes back to your original hazard identification analyses that you were taking, how you've identified the hazards, whether that's by hazard or HAZOP or LOPA or a combination of them or whatever. Yeah, and of course, the basis of safety may change over time because you make changes to the process or you make changes to the plant and so on and so forth. So your management of change system is also a key element of process safety management. And of course, all of that knowledge, all of that understanding should be fed into your process instructions and SOPs, your training, your audit systems, your emergency plans, and so on and so forth to make it a totally sound system. It isn't, basis of safety isn't just the technical equipment side of things. Yes, somebody's got to have used the correct codes to be able to size the vent, obtain the correct calorimetry data to be able to pull the data out to be able to size that vent and everything else. And if you've got competence lacking at any stage, then you'll lose it. I've gone slightly over time, but hopefully you found it enjoyable. You know where we are. If you want to contact me, happy, just send an email into info@Sigma-HSE. We can help you out on any of the sorts of issues that we've been talking about today. We've got the competence of designing basis of safety and the competence of getting all the data necessary. Okay, and with all of that, if we do have a really good understanding of what we're playing with out there on our plants and processes, the materials, the processing hazards, yeah, if we really do understand what the hazards and risks are, that the processes we've used to do our hazard and risk assessments are robust, that we've tried to design out or minimize hazards, then we can be confident that the safeguards that we've adopted on our given plants as our basis of safety will reduce the level of risk to a level that everybody, ourselves in the business and the regulator, should be happy with. So thank you very much for listening, and hopefully you'll come back and listen to me next month or the month after on the next webinar. So thank you very much for your time. Any questions, just send an email in and I'll happily reply to those. So have a good rest of the working day and see you soon. Bye-bye.